you're not asking questions. It would be good if you could wear masks. I think it would be better for everybody. So if you've looked at the recommended reading for the course, you have an idea of what most of the topics will be. So the first few weeks, we'll have to do with causal properties of general relativity. And the references were on the recommended readings. There's my article, which you can find it on the archive. The title begins with light rays and so on, singularities and all that. There's also Wald's book, where the relevant part is chapters 8 to 11. The difference between the two is that if you want more mathematical detail, you should look at Wald's book. In my notes and also in my lectures, you'll find more informal explanations. So even before you started studying general relativity, you all had a basic idea about Riemannian geometry, at least intuitively, because you're all quite familiar with curved two-dimensional surfaces. A curved two-dimensional surface is a reasonable prototype for Riemannian geometry in a positive signature. Of course, in general relativity, we're interested in Lorentz signature. And there are a lot of basic things, like the definition of the affine connection of the Riemann tensor and so on, which are the same independent of the signature. And so you can learn basics of general relativity up to and including things like the Schwarzschild solution and its predictions for motion of the planets, treating Lorentz signature purely by formal analogy with Riemannian signature. For example, that's the way I learned it myself from Weinberg's book, which is actually an excellent book on gravitation and cosmology. There are a couple seats in row 2 that will help with something. So, what's new in Lorentz signature? And doesn't have an analog in Lorentz in Euclidean signature is causality. And many of the most fascinating and puzzling aspects of general relativity have to do with the implications of causality. So that will be our focus in the first few weeks, which means we'll study topics like the formation of black holes and singularities. Then, and coming along with this will be the Hawking area theorem. We'll learn what's the problem, at least in classical general relativity, of the idea of a shortcut through the wormhole. And then we'll learn the, for example, what causality, we'll discuss causality in the context of the ADS-CFT correspondence. That's a big word which you won't all be familiar with. The bare minimum you need to know. I'll explain when we get to it. So anyway, our goal is to understand what's different about Lorentz signature from Euclidean signature, what you can't just learn by formally using the Euclidean formulas for the affine connection and the curvature tensor and the covariant derivatives. So for the starting point, we're going to consider causal paths in Minkowski space. Well, what's a causal path? Well, a path in general is described by giving space-time coordinates x mu. Let's say we're in d dimensions. with this kind of metric. And to give a path, we give the coordinates as a function of some parameter. But two paths that differ only by change of parameter are considered equivalent. A path is causal if its tangent vector is everywhere time-like or null. But we can if so, we can always orient the path to make it future-directed. In other words, after possibly replacing s by minus s, we can assume that dx mu ds is a future-directed. So now we want to consider 2 points in Minkowski space, P and Q. Let's say that P is to the future of Q. And we're going to look at the space of all causal paths from Q to P. Well, one obvious fact about a causal path is that it has to stay inside the future of Q, which is a kind of light cone. Well, a light cone together with its interior. Sometimes the phrase light cone is used to mean the cone itself, but here we mean the cone together with its interior. And we have also the path light cone of P. So the two cones intersect in what I'll call DPQ, which is called a causal diamond. The intersection of the future of Q with the past of P. So, any causal path. So, if gamma is a causal path from P to Q, then it's contained entirely inside DPQ. And DPQ is, of course, compact. So causal paths from P to Q can't get out of a compact set. But our first non-trivial result is going to be that the space of causal paths is compact. Which means that if you have any sequence has a convergent subsequence. This would be completely false without the assumption of causality. But to see that, let's, for example, consider Minkowski space in 2 dimensions. I'll call it M11, one space, one time. Although we're really interested in the Lorentz signature metric, I'll postpone that for a second. Then I'll take P to be the point 1, 0, T equals 1, X equals 0. I'll take Q to be the origin. And then an example of the sequence of non-causal paths from P to Q would be like XP sine of pi nt. That's not in parametric form, which I assumed over here. To put it in parametric form, we would just say that t is equal to the parameter, and x is sine pi nx. Anyway, if I define gamma n to be this curve, you see it is a curve from Q to P, but it wiggles n times. And the wiggles all have constant amplitude, and as n goes to infinity, it becomes wilder and wilder. So there's no reasonable sense in which such a sequence has a convergent subsequence as a path from Q to P. There's some fine structure in that statement that maybe will be a homework problem. Anyway. as paths from P to Q, there's definitely no limit. But suppose we had causal paths. So these are definitely not causal paths. These paths are mostly going in space-like directions, actually. When n becomes large, they're moving in almost at zero constant time, parallel to the x-axis. And even if I change the role of x and time, we have paths that they'd be zigzagging back and forth, so they would have space-like portions. So nothing like this is going to be a causal path, but how would you prove that a sequence of causal paths has a convergent subsequence? Well, here it's convenient to introduce a Euclidean metric. So even though we're really interested in the Lorentz signature problem, it's often convenient to consider an auxiliary Euclidean metric. I've picked one. I had to pick a Lorentz frame to do so. So this wasn't unique. If we made a Lorentz transformation to different coordinates, I could have written the same formula, but it would have been a different metric on the same Minkowski space. So I've picked a non-natural Euclidean metric that nevertheless is convenient in making the argument. Now, if we go back to our situation where P was 1, 0, and Q is 0, 1, 0, 0. In 2 dimensions, the causal path is just a square. Causality means that the tangent vector to a path is at no more than a pi/4 angle from the vertical. So you can see that the Euclidean length of the causal path, I'll call this Euclidean length L, is in a narrow range between 1 and the square root of 2 for this particular choice of P and Q. The straight line has Euclidean length 1, and you can't make length longer than going this way and then back this way, which would give you an extra factor of the square root of 2. So the Euclidean length is bounded above and below. And that means that we can parameterize a causal path by parameter S, which is a multiple of the Euclidean length. And we normalize it to go from 0 to 1. So in the case of these geodesic, we would simply let S be the Euclidean length parameter. In the case of this one, S would be the square root of 2, or sorry, 1 over the square root of 2 times the length. But anyway, since the length is bounded above and below, we can, in particular, it's always positive. We can do it as I do. At that point, we can completely forget causality, because that's enough to imply that such, consider our sequence, gamma 1, gamma 2, that we want to prove has a convergent subsequence. So we have x and t are functions of x, xn of s and tn of s. We should put t first. I'll try to remember to do that. Well, by definition, let me just call this x vector of s. By definition, x of 0 is 0, 0, and x of 1 is 1, 0. So even without taking a subsequence, we have convergence at those two values of s. Now, I'm going to make the argument that you might be familiar to all of you from whatever encounter you may have had with the fundamentals of calculus. So we look at the point x, s equals a half. So xn at s equals a half is contained in this square, which is compact. So there has to be a subsequence of values of n such that xn of 1/2 converges. So we replace the sequence xn of s but where we had convergence at x equals 0 and 1 by a subsequence which I call x and 1 of s, which has convergence at 0, 1/2, and 1. But then we do the same thing, adding points, let's say 1/4 and 3/4. At s equals 1/4 and 3/4, xn of s is again in this compact square. So again, we can extract a subsequence so that xn converges at both 1/4 and 3/4. As the third step, we extract a subsequence that converges if s is an integer over 2 cubed. Can you see in the back, or am I writing too small? That's okay. Then we keep going, and at the kth sequence, or sorry, the rth sequence, we have convergence if s is of the form k over 2 to the r. And then finally, we pass through the subsequence x and n. In other words, the so-called diagonal subsequence, x11, x22. Maybe I'll put columns here because I can notice. x33. So now, the nth element of this sequence has r equals n, so it converges if the denominator is 2 to the r. But that's true for all r, because except for finite remaining exceptions, these are all in the rth. I draw the nth element of this final diagonal sequence from the nth row in this picture. So that means that we have conversions at all we have convergence at k over 2 to the r for all positive integer k, or non-negative integer k. So we have convergence at a dense set of points. But since we parameterize these curves by the Euclidean arc length, nothing wild can happen between that dense set of rational numbers. So actually, this sequence is convergent. So we've proved that unlike while a completely generic set of sequence of curves would have, in general, would not have a convergent subsequence, causality ensures the existence of a convergent subsequence. Now, you're going to gradually see that that's powerful and useful. It might not be immediately obvious, but I'm going to first use it to draw a trivial corollary, which is something that you already know, but just to illustrate the idea. If you have a causal path, it has an elapsed proper time. And that's a function on the space of causal paths. And since we learned that the space of causal paths, it has to be bounded above on the space of causal paths. Because if there were a sequence of causal paths where tau goes to infinity, such a sequence could not possibly have a convergent subsequence. Given that it's bounded above, now you look at any sequence of causal paths where tau approaches its upper bound, and a convergent subsequence of that is going to have to be a maximum of tau. So we learn that there exists a curve, a causal curve, of maximal tau. But I can demystify that. That's simply equal to the geodesic from Q to P. The condition for a curve to extremize the proper time is that it's a geodesic. And slightly non-trivial fact, but a true fact, is that in Minkowski space, a time like geodesic always maximizes the proper time. That statement is kind of called the twin paradox. The one who stays at home, traveling on a geodesic, ends up older than the one who took a trip, because the geodesic maximizes the proper time. So we kind of, in drawing this corollary from our compactness statements, we prove something you already knew, but eventually we'll use the same argument in curved spacetime to prove Hawking's theorem about the Big Bang. That'll be a more interesting application. Well, yes?
Proof that the space of causal paths from P to Q is compact. I believe we use the auxiliary Euclidean metric, right?
Yeah.
I read Walt before, and he also does the same. Is there a way, all the proofs use that, or is there a way to, or?
I don't personally know a proof about using an auxiliary Euclidean metric.
Okay.
Any other questions? Yeah?
Can you explain why there's a causal curve with maximum tau?
First, tau has to be bounded above. Because if there was a sequence where tau could go to infinity, it would clearly have no convergent subsequence.
Yep.
We proved compactness. Now that you know the tau is bounded above, consider a sequence that converges. Now we want to show that the maximum is actually achieved. Right? It's bounded above, so there's a least upper bound. Is there a curve that has that least upper bound? Well, consider a subsequence whose, since it is the least upper bound, that means there's a sequence whose proper times are convergent to that value. That sequence will have a convergent subsequence, and the limit will be a curve that actually has the least upper bound as its proper time. I'd like to say that, this argument is definitely, well, it's in Wold's book as well, but you'll certainly find my version of it in my lecture notes. And the same goes for most of the arguments I'll be explaining, many of which are explained in more detail in the written version than I can really present in the lecture. If you look carefully at some footnotes in the lecture notes, by the lecture notes I mean the article, light ray singularities and all that, you'll see that there's some fine structure that I'm sparing you. It would be too tricky. There are a few details that would be too tricky to explain in the lecture. Any other questions? Now, this was Minkowski space, but in what class of spacetimes could we have made a similar statement? Well, the only fact we used really was that dpq equals the past of P intersected with the future of Q is compact. By past and future, I mean points that can be reached by causal paths, either null or time. Sometimes one distinguishes the time-like future from the causal future. Here I mean the causal future. So we used the fact that the causal diamond was compact. That was the only important fact in the argument. So a similar result is told in any space-time where causal diamonds are compact. But what kind of space-times are those? So I first want to give a couple of examples of space-times where causal diamonds are not compact. And then we'll introduce a useful condition that ensures that they are compact. So one example is going to be slightly artificial, and the second one is a more natural example. So for the slightly artificial example, I didn't quite write down the definition of the space-time. I was intending to at the beginning, but I forgot. Space-time is a Lorentz signature manifold. Smooth manifold. So now I'm going to give a simple example, an almost trivial example of a space-time where the causal diamonds aren't compact. Take Minkowski space. It could be in any dimension, but I'll take 2 dimensions so I can draw a picture and remove a point. So here's P, here's Q, and now I remove a point, R. It's hard to draw removing a point. I've drawn a little circle. It's meant to not look like a dot, it's meant to look like a little hole. But I've tried to draw big enough that people in the back can see that it's a little hole. And this is a space-time because removing a point does not affect the fact that we have a Lorentz signature manifold. But clearly, the causal diamond is no longer compact. And equally clearly, it's no longer true that a sequence of causal paths will have a limit. Because we could consider a sequence of causal paths from P to Q that in Minkowski space would have had a limit that passes through the point R. But in this space-time, it has no limit. So this is an example showing that if the causal diamond is not compact, in general, the space of causal paths is also not compact. Now, you may feel I've cheated with this example because it seems highly artificial. I can make it seem more natural as follows. Let phi be a function on Minkowski space that blows up at R. And consider the Weyl rescaled metric, not minus dt squared plus dx squared, but minus dt squared times dx squared times e to the phi. That's called a Weyl rescaled version. Multiplying the metric by a positive function is called a Weyl rescaling of the metric. A Weyl rescaling does not affect the condition for the path to be causal. So as long as the function phi is a smooth function, the space of causal paths is the same as it was before, and it's still compact. However, suppose that the function phi blows up at the point R. Then we have to remove the point R, or we would not satisfy our definition of a space-time, which is required to have a smooth manifold with a smooth Lorentz signature metric. So for this space-time, there's a rationale for omitting the point R. And since, so therefore this space-time is a relatively natural example of a space-time where the causal diamond and the space of causal paths is not compact. Any questions on that example? The second, okay, so what about the corollary we drew from compactness, which is that there's always a path of greatest proper time from Q to P. That will actually be true generically, but not always, because if the point R that we removed happens to be on the geodesic, well, I have to be more careful because in general this will change the geodesics. You could arrange so that phi has a symmetry exchanging the two sides of the picture. If phi has a left-right symmetry, then if it doesn't blow up, the straight line from P to Q to P will still be geodesic. What if it does blow up? The point you've removed is trying to be on the geodesic from Q to P, and there will be no path of greatest proper time from Q to P. In fact, because of the what will happen is that because of the blow-up, pairs that go nearby R can have very long proper time. And for suitable function phi, there will be no upper bound on the proper time elapsed between Q and P. which certainly implies that there's no path that maximizes the property. Okay, the second example, well, is one that people interested in quantum gravity study a lot, namely anti-de Sitter space. But to keep things simple, I'm going to just what I'll say is true in any dimension, but to write simple formulas and avoid any extraneous details and have nice pictures, I'll just do it in 2 dimensions. So anti-de Sitter space is the solution of Einstein's equations with negative cosmological constant and maximum symmetry. But concretely, it's described by this metric. Where t goes from minus infinity to infinity, but sigma goes from 0 to pi. So anti-de Sitter space is a strip. Sigma equals 0 is on the left boundary. Sigma equals pi is on the right boundary. And time goes vertically. The boundaries at sigma equals 0 to pi can't be included in the space-time because the metric blows up there. And more fundamentally, because the distance diverges. If you go toward the boundary in the sigma direction by integrating the sigma over sine sigma from A down to epsilon, you'll see it diverges as epsilon goes to 0. So the boundaries are infinitely far away if you try to get there along a space-like path. However, suppose you try to get to infinity to the boundary of a light-like path. Then the Weyl factor in front has no bearing. The metric is equivalent for light-like paths to a strip in Minkowski space. So a light ray would just travel at a pi over 4 angle to the vertical. And you can reach infinity and back in a finite time. This is something which is quite familiar to those of you in the audience who have worked on the so-called ADS-CFT correspondence. But anyway. Now, continuing with this example, let Q be that point, but in fact, although not manifest in the way I wrote the metric, this is a homogeneous space-time, so Q could have been any point. In other words, for any point, we could pick coordinates. Well, I didn't even tell you what its coordinates at this point. Maybe t equals 0, sigma equals pi over 2. But whatever they were, it doesn't matter because it's a homogeneous space-time. Now you could ask for different choices of P for is the causal diamond compact? And you'll see that if P is slightly to the future of Q, well, for that choice of P, the causal diamond is that rectangle that's certainly compact. And in fact, a little thought will show you that as long as P is in the interior of the square, the causal diamond is compact. I could put P up here. Well, let's call this one P1. For P2, I'd have the bigger rectangle. But as soon as P is outside that square, let's say P3, the causal diamond dQP3 is not compact. Because a causal path from Q can get as close as it wants to the boundary before going to P3. Remember, the boundary points are not part of the space-time. They can't be, because the metric blew up there and those points are infinitely far away. With our definition that a space-time is a smooth manifold with a smooth Lorentz signature metric, we can't include the boundary points. But in the picture they include them. It's convenient to include them, but they're not. It's convenient to include them in the picture and in many mathematical arguments, but they're not points in the space-time. So causal path can come arbitrarily close to the boundary in this picture, and that means that the space of causal paths can't be compact. A sequence of causal paths that's getting closer and closer to the boundary won't have any convergent subsequence. Or just more brutally, what the causal diamond is, well, it's the interior of this five-sided picture, except that one boundary is missing. So it's got four closed boundaries and one missing boundary. Now, what's the maximum elapsed proper time on a causal path from Q to P3?
There is none.
What's that?
There is none.
Well, there's no upper bound, because if you travel very close to the bound, it's similar to this example we had before, where for suitable functions phi, a path that goes very close to R in the picture can have arbitrarily big proper time. Likewise, here, if you go sufficiently close to the boundary and stay there for a while, you have a very large proper time, and there's no upper bound on how big that proper time can be. So there's no upper bound on the proper time elapsed from on a causal path from Q to P3. In particular, there's no geodesic that maximizes the proper time. In fact, the stronger statement is that there's no geodesic at all from Q to P3. That's not obvious from what I've told you. I think we won't really use it. I'm not planning to prove it. You can find it explained in an appendix in my lecture notes. So these are a slightly artificial and a more natural example where the spaces of causal paths fail to be compact and there isn't any upper bound on the elapsed proper time of a causal path. And as you're going to see, it's important to know about such compactness and such an upper bound. So we're going to be interested in criteria under which things are well made. So what we're going to navigate toward next is a discussion of a general condition that will lead to good behavior. So first of all, we have the following local facts about Minkowski space. Which is that, sorry, about general relativity. Or if you like, a local fact about Riemannian geometry. Here we're going to be, for a moment, back in the realm of statements which are equally true in Euclidean signature or in Lorentz signature. Well, I'll save it for Lorentz signature. But with a couple changes of words, the same thing is true in Euclidean signature. So each point has a Q, let's say, has a small neighborhood UQ that is well approximated by Minkowski space. Sorry, a neighborhood in Minkowski space. So there are different aspects to being well approximated, but one useful statement is that each point Q has a small neighborhood with the property, it's called geodesically convex. If you're given any 2 points in that neighborhood, there's a unique geodesic between them that's contained in the neighborhood. So that's it. If we're in Minkowski space, a causal diamond has that property, for example. Given any 2 points in a causal diamond, well, first of all, any 2 points in Minkowski space are connected by a unique geodesic anyway. But if you have 2 points in a causal diamond, the geodesic between them is contained in that diamond. The diamond is convex. So, in general relativity, given any point, it has a small neighborhood that's well approximated in any reasonable sense by Minkowski space. The metric is almost flat and can be approximated by a piece of the Minkowski space metric. And also there's this geodesic property that every point has a sufficiently small neighborhood that 2 points in that neighborhood are connected by a unique geodesic in that neighborhood. So, and we're going to call this a local Minkowski neighborhood.
I have a quick question.
Yes.
So I assume that does S need to be in the future of R? When
No.
you choose?
Well, I didn't say the geodesic was time-like. In Minkowski space, every 2 points are connected by a unique geodesic, but it might be time-like space like a null. And same here. This statement held for any 2 points, regardless. Okay. So there's something we'd like to be true that isn't true without imposing a further condition on space-time. So let Q be a point. So M, I think I'll use as a generic name for space-time. And P slightly to the future of Q. You can take that to mean that there's a geodesic from Q to P that's time-like with small proper time elapsed. So here's a question. This is a kind of trick question. Well, is DPQ compact? So, one's intuitive feeling of what space-time should be would tell us that if P is slightly to the future of Q, dpq should always be compact. But it was in the 2 examples I gave you. For example, in this one, we removed a point, but a point slightly to the future of Q as a nice compact causal alignment. And also, that was also true with the anti-de Sitter example. So you might hope it would be true in general, but it's not true without a causality condition. So here we need a causality condition. And you see, what makes this obvious is that we at least need the condition that there are no closed causal curves. From Q to Q. Because if we have a closed causal curve from Q to Q, well, you see, a closed causal curve. The intuitive idea was that dpq was supposed to consist only of points in the small region between P and Q. That was the picture I drew. But if there is a closed causal curve from Q to Q, in general we know nothing about where it goes. It might go to a region of space-time where a point was missing, or where there was an anti-de Sitter boundary, or where anything bad could happen. So if there's a closed causal curve from Q to Q, any point on that curve is in the future of Q and also in the past of P. Because we can make a causal curve from Q to P that first goes around the loop and then goes on to P. So we at least need to have no closed causal curves in space-time if we want it to be true that dpq, well, this shows that we need, that's not universally true. We need some condition on space-time to make it true that dqp is compact if p is slightly to the future of q. So to get a nice statement, we need no closed causal curves. But we need a slightly stronger condition, which is called strong causality. Strong causality says that not only there are no closed causal curves from Q to itself, but there are no causal curves that come arbitrarily close to returning to Q. Because if you could have causal curves that come arbitrarily close to returning to Q, so you go through such a curve, then go on to P. Again, you'd explore a region of space-time that you know nothing about. So you wouldn't be in the situation where dqp is contained in a local Minkowski neighborhood. So it's reasonable to consider spacetimes like this to be pathological, but we do need to exclude them. So a statement that's simpler than what I wrote in my lecture notes, but kind of in hindsight wish I'd written, is in my lecture notes and also in Would's book, you can read the definition of strong causality, explained more carefully than I have. But the purpose is to ensure that if P is slightly to the future of Q, and I remind you that means if P is close enough to Q along a time like geodesic, then dpq is contained in a local Minkowski neighborhood. So that's going to be false in general if we have closed time-like curves, because such a closed time-like curve will consist of points to the future of Q and the past of P, and then we won't have any control over where it goes. So this is a nice condition on a space-time. I feel in hindsight that I kind of wish I had taken this as the definition of strong causality. When I wrote those lecture notes, I really wanted to get rid of technicalities. And this is one point where I got tangled up, and I was really not happy with what I wrote. And after thinking about it for a couple more years, I think that instead of proving that this follows from strong causality, which is not fun, I should have just taken this as the definition of strong causality. Okay, but anyway, if P is slightly to the future of Q, then we in a reasonable space-time, dpq is compact, and therefore the space of causal curves is compact. Because we've understood that the space of causal curves will be compact, whatever dpq is compact. Whatever the causal diamond is compact. But we want to say something when P isn't just slightly to the future of Q. And that will be presumably the rest of this lecture and probably a good part of Thursday. So what if P is not just slightly to the future? So we're now going to discuss a causality condition that's much stronger than the absence of closed time-like curves. It's also much stronger than strong causality, regardless of which definition of strong causality you take. And it's the most important causality condition in general relativity. And this is the condition for space-time to be globally hyperbolic. So the intuitive idea is that a globally hyperbolic space-time is one in which everything can be predicted based on initial data on some initial value surface S. So here's space-time. S is a space-like surface. Sometimes it's useful to let S have null portions, but for our lectures, S will be space-like. And we want to condition on S such that everything that happens in space-time is knowable from conditions on S. So, well, so one definition is that one part of the definition is that S is space-like. Another point is that every point in non-S is to the past or future of S, but not both. So that means, so every point in space-time can be reached from S by a causal curve of some kind. And that will either be a future-going causal curve from S to P, or to a point, or a future-going causal curve from the point to S. But not both. If we assume that the condition that no point is both to the past and to the future of S is similar to saying that there are no closed time-like curves. But the third condition is the key one. We need an additional condition which will ensure that every signal that you see anywhere in the space-time can be computed from a knowledge of what there was on S. So if you're sitting at a point P and get a signal, where did it come from? Well, it presumably got to you along a causal path. That's what it's supposed to do in general relativity. So you'd like to know that each causal path can be continued backwards until it came from S. So let's say if P is to the future of S, to predict physics at P, based on what there was on S, what you need to know is that every causal path that arrives at P can be continued backwards until it reaches S. Well, let me give an example where this condition is not satisfied, and that might make it more obvious. Suppose I take a globally hyperbolic space-time like Minkowski space. Well, we'll check in a moment that Minkowski space is globally hyperbolic. Take a space-time where it's true that every causal path can be continued back until it reaches S, and remove a point. As before, you can make removing a point less unnatural by making a violent rescaling to a metric such that that point couldn't be included. Then you'll see that there could be a causal path that originated at R and can't be continued until it reaches S. It gets stuck at the point R. If that happens, you cannot predict physics at P based only on a knowledge of initial data on S. There could be a signal that originated at R. So if you want to be able to predict the physics of P based only on initial data on S, what you need to know is that every causal curve can be continued until it reaches S. That's the third and possibly technical sounding statement of the definition of global hypervelocity. But it's, since a signal could have arrived at you on any causal path, a signal that couldn't be continued until it reaches S can convey to you a signal that doesn't know what there was on S, or can't be determined from what there was on S. So that's the motivation behind this condition. Any questions about the definition? So for example, let's check that Minkowski space is globally hyperbolic by this definition. We can take S to be, for example, a hypersurface T equals 0. So first of all, every point in Minkowski space that isn't at T equals 0 is either positive or negative T, so it's to the past or future of S. Secondly, every causal path, let's say if you start at the future of S, for example, positive T, a backwards going causal path is moving backwards in time at a rate, it's moving backwards in time, and it can always be continued until it reaches time 0. You can always keep going farther backwards in time until you reach time 0. Likewise, if you start in the past, any causal path can be continued to the future until it reaches time 0. So Minkowski space, if you like, is the prototype of the global hyperbolic spacetime. So, if we take this example where this example here is meant to be, here I took a wiggly surface. Obviously in Minkowski space, time 0 was good, but any wiggly surface that wasn't too different from time 0 would have been equally good. However, if you take, so we have a globally hyperbolic spacetime and remove a point, we get to a situation where from data on S, we can't predict everything throughout the spacetime. We can't predict data that's to the future of the point we made. But the rest of the spacetime, as a tautology given any S, keeping take any space like hypersurface S and take a point slightly to the future. By our strong causality assumption, things are well behaved. So backwards going causal paths that don't go very far are contained in a local Minkowski neighborhood. So if we just include a point slightly to the future in past of S, we get a globally hyperbolic spacetime. In this example, if we throw away everything to the future of the missing points, the rest of the spacetime is globally hyperbolic. So, what's called the domain of dependence of S is the subspace of M, which is the largest globally hyperbolic one. It consists of all points with the property. So if S is not an initialized surface of a globally hyperbolic spacetime, there will still be points with the property that any causal path from that, going backwards from that point, reaches M. Or if you start in the past, that everyone going to the future reaches M. The set of all such points is called the domain of dependence. And the boundary of M prime is the, I think a better name, M prime, I'll call it curly dependence, the domain of dependence S. Its boundary is the Cauchy horizon.
Question.
Well, I should have said here that such an S is a Cauchy hypersurface. Well, I'll use as synonyms the phrases Cauchy hypersurface and initial value surface. Yes?
Is condition 2 equivalent to strong causality? Or can it be replaced by strong causality? In other words, suppose you have a space-like surface, but condition 2 is not satisfied.
Yes.
then presumably something bad, those kind of curves means that.
Definitely something bad, something.
What I mean is,
No.
can you do the same construction of the
No, no, that's
domain
not, it's not
dependent?
equivalent. Well, without further discussion, it's not equivalent to strong causality. For example, take a Lorentz signature cylinder. The metric is just minus dt squared plus dx squared. But x is equivalent to x plus 1. It's an excellent spacetime. It obeys every reasonable causality condition. It's globally hyperbolic if you pick this S. But now suppose we pick an S that wraps around. The condition it doesn't satisfy is that every point, now a point is both to the past and the future of S. So this part of the condition was not just a condition on the spacetime, it's a condition on S.
I see. Thanks.
Any other questions? Okay, I wanted to give another example of a domain of dependence in a Cauchy hypersurface. So, just to make it easier to draw, we'll do two-dimensional Minkowski space. And this kind of surface is a Cauchy hypersurface. But now take this kind of surface, a hyperboloid. It's not a Cauchy hypersurface because a causal path, here's an example of a causal path that never reaches S. A causal path could be asymptotically parallel to this vertical, sorry, to this diagonal line, and it never reaches S. So such an S is not a causal, not a Cauchy hypersurface. And you can ask what's its domain of dependence. It's not hard to see that the domain of dependence is the future light cone of the origin. Every point to the future of the origin has the property that a causal path through that point can be extended either toward the future or the past until it reaches S. And the Cauchy horizon of S is the light cone itself as opposed to its interior. So D of S is the future light cone of the origin plus interior. And the Cauchy horizon is the future light cone. So if you're given initial data on S, you can predict a solution of, for example, Maxwell's equations throughout the future light cone of the origin, but you can't predict what there is outside that. Any more questions on this before we go on? Now, how is global hyperbolicity related to the first part of the lecture? The answer to that question is that I should have asked if the people in the back can hear as well as see. Okay. In a globally hyperbolic spacetime, spaces of causal curves are compact. this is what I want to explain next, although I don't think we'll finish it today, actually. When there are two versions of this statement. One is that the space of causal curves from Q to P is compact. Well, when I make this statement, we consider the empty set to be compact. If Q isn't to the future of P, if P isn't to the future of Q, there might be no causal paths from Q, future no causal paths from Q to P. So this set might be empty. We won't treat that as an exception. The statement is that for any 2 points, the space of causal curves from between those 2 points in a globally hyperbolic spacetime is compact, possibly empty. It might consist of only 1 point, but it's always compact. There's a related statement. Instead of a causal path between 2 points, you can consider a causal path from a given point to a Cauchy hypersurface S. So I'll write CQS for the paths from Q to S. And likewise, CSQ for the paths the other way around. I always put the, I consider as a convention, future-going causal paths. And they're future-going from the one at the bottom to the one at the top. So here I'm considering either paths between 2 given points, or paths between a given point and a given Cauchy hypersurface. So, in a globally hyperbolic space-time, the claim is that these are all compact. And as I say, explaining that is going to be the next goal. After which, we'll start learning about why that's useful to know. So, in Wald's book, and before that in Hawking and Ellis, there's a proof of this that uses Zorn's lemma. I really didn't like it, because this concrete statement like this shouldn't depend on exotic statements in set theory. And I really spent a lot of time unsuccessfully trying to find a proof that didn't use Zorn's lemma. And finally, although I failed, I found one in the math book by Ehrlich and others. You'll find the reference in Appendix D of my lecture notes. And what I finally wrote, which you can find in the appendix, is the Zorn-based proof of Hawking, Ellis, and others, but I also explained the non-Zorn proof of Ehrlich and others. And I decided for you we're going to do the non-Zorn proof, because I was happier with it. And it does require explaining a preliminary, which, however, is a preliminary we'll also need to know later. So, the preliminary that we can know is that any manifold M I'm putting any in quotes because if you're too abstract about manifolds, you can have extremely wild topology. I don't want to formalize what exactly we mean by a manifold to keep it from being too wild. But any manifold M has a complete Euclidean metric. We're going to use that as a lemma from which we'll rather, in a surprisingly simple way, deduce the fact that spaces of causal curves are compact in globally hyperbolic Lorentz signature spacetimes. How do we know that any M has a complete Lorentz signature metric? Well, first of all, here's the M. Well, first we should know that any M has some metric. Any M has some metric because metrics can be added. By definition, any M is equivalent to an open set in. So any M is locally equivalent to an open set in some Euclidean space. So we cover M by open sets, so in each open set, take some metric that's non-zero in that open set, and then just brutally add them all up. So the first step is that any M has some metric. Well, at that level, we might have picked a metric that wasn't complete. So what does complete mean? Complete Riemannian metric means that every geodesic can be extended to have infinite length in both directions. So for example, Rn is complete. A geodesic is a straight line. It has infinite length in both directions. So what we're going to be studying, in effect, following Penrose and Hawking, is how completeness fails in Lorentzian visual geometry. But for orientation, we should be familiar with what completeness means. So I think I was erring in skipping over the definition of completeness. Completeness, for Riemannian metrics, completeness means that the geodesic can be extended to have infinite length in both directions. By some definitions, you could take a piece of a geodesic and call it a geodesic. But if you've done that, you could have extended the geodesic to its maximum possible length, and that length is infinite in both directions. Now, so NEM has some metric H. And then the second step is that there's some function phi such that G equals e to the phi times H is complete. Well, how would you make that happen? Well, roughly speaking, you want phi to blow up near infinity on A. So you want to have a measure of how far you are from the boundary of M, and then phi should be 1 over that distance. So how would you measure how far you are, in a completely general Riemannian manifold, how would you measure how far you are from infinity? Well, you take a point P, and you take the shortest geodesic that can't be extended further. If M was already complete, the distance of every geodesic can be extended up to infinite length. So this function would be
on that
infinity.
point, what about the great circle on the sphere? Do you just keep on going?
Yes,
Okay.
you're allowed to.
It's a lot of keep on going. Right.
To clarify the question for everybody, a geodesic is not required to be embedded in space in M. As in the example of a great circle in a sphere, it goes around. But it can be continued to infinite length in both directions. It's retracing its steps, but that's allowed. A geodesic is a solution to the geodesic equation. Luckily, it's embedded in the manifold, obeying the geodesic equation. And it continues to infinite length in both directions. So, if M is complete, then for every point P, every geodesic can be extended to infinity in both directions. But if M is not complete, there will be some P's which have some distance from the boundary, meaning that there's a shortest inextendable geodesic from P. So I'll call its length D. So D is either a positive real number or infinity. And then we just think we just phi d e to the d of x times h. And since it blows up near the boundary, we've achieved the situation where the metric is now complete. So you can find this argument explained a little bit more precisely in an appendix of my lecture notes. Any questions about that? So now there's a compactness statement for inextendable curves in any complete Riemannian metric. Like gamma 1, gamma 2, and so on. Be any sequence of inextendable curves That's all start at the same point P. So here's gamma 1. Here's gamma 2. Here's gamma 3 and so on. Gamma 4 must be this. As in Nemo's comment, one of the gammas might loop around without ever going to infinity. Some of them go to infinity, some don't. The gammas are any sequence of inextensible curves from P. They all have infinite length. They all have infinite length in the Euclidean metric. Because in a complete Riemannian manifold, a curve of finite length, and somewhere inside the manifold, it can be continued further. The claim is that any such sequence has a convergent subsequence. How do we prove that? Well, so let B and B, the set of points in M of distance equal to or less than M from P. In a complete Riemannian manifold, that's going to be compact. Because if a point has a distance, a point will have a minimum distance from P. That'll be its distance along the shortest geodesic. What are the points that can be reached along a geodesic of length at most n? Well, you start at P, you get to pick a direction. The space of directions is compact. Then you travel at most a distance n along a geodesic, that's also compact. So the set of points you can reach by a geodesic of length at most n is compact. Now, if a point has a distance no bigger than n from P, meaning it can be reached by P from some curve of length no more than n, then there will be a geodesic connecting that point to P that's only shorter, if anything. So the shortest geodesic connecting a point in Bn to P always has a length at most n. So Bn is compact. So if we have our sequence of these points, curves, gamma 1, gamma 2, which are all curves from P, restrict them to Bn. Well, restrict them to B1 first. Let me say this a little bit differently. So we parameterize the gamma I by arc length S. And it goes from 0 to infinity because, as I remarked, an inextensible curve is going to have infinite length in a complete Riemannian manifold. So, first, restrict to S equal to less than 1. That means the restriction is now contained in B1. And B1 is compact. And now we're in a situation we were in about an hour ago. We have a sequence of curves with the same starting point in the compact manifold. So by the same logic I told you before, there's a subsequence, gamma 1, 1, gamma 2, 1, gamma 3, 1, that converges for S equal to less than 1. But then we can do it again. Now restrict to S equal to or less than 2. And so there will be a further subsequence, gamma 1, 2, gamma 2, 2, gamma 3, 2, that converges for S equal to or less than 2. At the nth step, we'll have a sequence gamma 1 and gamma 2 and gamma 3 and that converges for S equal to or less than n. And then the last step is the same as it was before. We look at the diagonal sequence. Gamma n, it converges for all s. Because it's a subsequence of the sequence of gamma 1 n's for every n. Or it is more precisely, except for a finite number of exceptions at the beginning. Yes?
How is it being guaranteed that as you increase the size of the ball, that the specific limit of the curves that we're choosing doesn't change? For example, ball of size 1, maybe it's this curve.
Here we have a subsequence of the original sequence.
Yes.
This is defined as a subsequence of this sequence.
Ah, I see.
This
Thank
is
you.
a
Yeah,
subsequence of this
I
sequence.
understand.
So, at the nth step, we've assured convergence inside the bowl of radius n.
Yeah.
Or, sorry, for the up to length n of the curves. Which is weaker than inside the bowl of radius n, which I don't know. The curves might not be expeditiously going far away. At the nth step, we have convergence up to s equals n. And we're always picking a subsequence of what we had before. So we get convergence up to infinity. So we've learned, and I will stop here except for questions, that every space-time has a complete Riemannian metric. And, okay, we've learned that in every manifold, every sequence of inextendable curves with a fixed starting point has a convergent subsequence. There was no mention of causality. We will go back at the beginning of the next lecture to the Lorentz signature context and deduce compactness of causal spaces of causal curves in a Lorentz signature spacetime. But we'll stop here, except if there's a quick question or two. Yes?
I have a quick question about the proof that every manifold has a complete Euclidean metric.
Yes.
We seem to be worried about the case where there's a boundary constructed this way and kind of eliminating that issue. But even on a manifold without boundary, couldn't you a priori imagine that there's some curve that looks spiraled in?
First of all, the manifold didn't literally have a boundary. Because by definition, a manifold has every point has a neighborhood isomorphic to an open set in Minkowski space. So when I use the phrase boundary, I'm speaking loosely. There were not boundary points in them. And was a manifold. What's that?
Is it just boundary of that set?
Well, the precise definition is that for point P, we define a function which was the length, the shortest length of a geodesic from P that can't be extended further. It's informal to say that that's the distance of P from the boundary of the manifold. The precise definition is what I just said about the length of the shortest inextendable geodesic. So there weren't boundary points. You can add them to draw pictures, but they're not part of the manifold. It's hard to draw a picture without drawing Otherwise, the picture has to go off completely. Yes?
So, like, when you say there's a manifold and Euclidean metric, what are those, like, arbitrarily creating this metric that's Euclidean, done by multiplied by e to the phi, that do you get h arc length? They don't have to be necessarily related by a coordinate transformation, right?
The first step was to construct submetric on M, which is possible because M locally is a subspace of Euclidean space, so it can certainly have a metric locally. And secondly, the Euclidean metrics can be added indiscriminately. The only condition on the Euclidean metric is that it's n by n positive definite symmetric matrix. The sum of two has the same properties. That's not true in Lorentz signature. So in Lorentz signature, it would not be true that every manifold has a metric. But Euclidean metrics can be added, so trivially, every manifold had a Euclidean metric. That was the first step in the argument. So So we just got some metric h, perhaps a very bad one. Then we improved it to either the phi times h, which is a good metric, a good starting point. We didn't care very much what it was. It was not very natural. It was a complete metric, but otherwise we didn't have any interest in what it was. So we're not really interested in trying to pick it more specifically, since any complete metric was adequate for the argument. Any other questions? Okay, we'll call it later and see if there's